Chapter 3 starts off with kind of a review of stuff I do in both Math 114 College Algebra Prep and in College Algebra. So you might be used to some of this stuff. You might have at least seen it once, possibly twice. Doesn't mean you remember it, but it's not particularly hard, the theory that we need to just review. And I just typed some stuff up so I didn't have to write it. I said a point is called a relative or local maximum point provided that it's higher than any point close to it. And the local maximum value or the relative maximum value is the y-coordinate of a relative maximum point. Relative and local we can use interchangeably, kind of depending on the text you pick up. I don't know that there's like a universal consistency between the word relative maximum and local maximum. Even like when I was scrounging Google for images, I saw equally relative and local maximums, and so they're both acceptable words. But a relative maximum point, which I have featured here, is a point that's higher than any point close to it. So this point is the point x equal -2, y equal to 58. It's not actually the highest point of the graph because the graph goes up forever. There's points higher than the point -258, but relative to any place close to it, it's the highest point. And so it would be proper to say this: the point -258 is a relative maximum point, or we can say local maximum point, and the relative maximum value is the y-coordinate. The y-coordinate of 58 is the maximum y value of any point close to it, and it occurs when x is -2. A relative or local minimum point is lower than any point close to it. And on my graph here, this point 3, -67 is called a relative or a local minimum point. Again, it's lower than any point close to it. Any point directly close to it is higher than it, but it's not the lowest point on the graph. The graph goes way lower than the point -3, +3, -67. Both maximums and minimums have points and values. The relative minimum point is the point 3, -67, and the y-coordinate of the minimum point is the relative minimum value. So for the minimum point, we can say the point 3, -67 is a relative minimum point, or I could say local minimum point. And the relative minimum value is -67, which occurs when x equal to 3, which means any point around this, its x may be bigger, its x may be smaller, but all the points around this, their y's will be bigger. So we're going to need to be able to describe regions of the graph on either side of the maximum and minimum points and between the minimum points. And so for this graph that I showed in the last screen, I need to be able to describe, just in terms of x's, the region to the left of the relative maximum point. I need to be able to describe the region to the right of the relative or local minimum point. And I need to be able to describe the region between the maximum point and the minimum point. It's going to be an important skill to be able to, once you identify maximums and minimums, separate the graph into regions and describe those regions how they need to be described. The regions need to be described in terms of x's and not y's. And for this first region to the left of the maximum point, I'm assuming this region continues on forever to the far left edge of the x-axis. So it starts at x equal to -infinity, and it ends at the maximum point x equal to -2. So this first region, the region to the left of the relative maximum point, I would say it starts at x equal -infinity and it ends at x equal to -2. When we describe the regions to the left of a maximum point, to the right of a minimum point, or between maximum and minimum points, we use round parentheses. The region to the right of the relative minimum point, it starts at x equal to 3. And I'm assuming this region goes on forever to the far right edge of the x-axis, and the far right edge of the x-axis has an x-coordinate of infinity. So the region to the right of the relative minimum point, we describe it as the interval from 3 to infinity. And then between the maximum and the minimum point, the region starts, the middle region starts at the x-coordinate of the maximum point, which is -2. It ends at the x-coordinate of the minimum point, which is 3. The region between the maximum and the minimum point, I'm going to describe using the interval -2 to 3. That's an important skill. Once we can identify maximum and minimum points, to be able to segment the graph into regions using round parentheses is going to be an important skill as we get into this section. Specifically, because we're going to be asked to find the intervals where the graph of a function is increasing, and we're going to be asked to find the intervals where the graph of a function is decreasing. A graph of a function is increasing in an interval where the slope of the tangent lines are positive, or where, as I'm drawing it, my marker goes up as I'm drawing from right to left, from left to right. This particular graph that I have shown on the screen, it has two intervals or two regions where it's increasing. The region to the left of the relative maximum point is called an increasing interval, because as I was drawing, just naturally drawing, my marker was getting higher as I was doing that drawing. Similarly, the region to the right of the minimum point is also considered an increasing interval, because just as you're drawing naturally, if your marker is going higher, pulling away from you, that's an increasing interval. If you're drawing and your marker is getting close to you, that's a decreasing interval. So these two outside regions are considered increasing intervals. And the region between the maximum and the minimum is considered a decreasing interval, because as I'm drawing, my marker's going down. As my marker's going down, the y's are getting lower, for what that's worth. So between the max and the min, this is considered a decreasing interval. This we do in college algebra, but we don't attach the tangent line concept. If I drew a tangent line at any point in an increasing interval, the tangent line is going to have positive slopes. If I drew a tangent line to any point in a decreasing interval, the tangent line is going to have negative slopes. That's a big deal when we go to use calculus to find where a graph is increasing and where a graph is decreasing. We need to know slopes of tangent lines are positive when a graph in an increasing interval, slopes of tangent lines are negative in a decreasing interval. That's a big deal. So for this particular graph, I'm going to find these intervals again. The first interval to the left of the maximum point goes from x equal -infinity to the x-coordinate of the maximum point, which is x equal to -2. The region of the graph to the right of the minimum point, this minimum point has an x-coordinate of 2. The region of the graph to the right of the minimum point starts at the x-coordinate of the minimum point. I'm not really sure what the minimum point is. I guess I wrote them down here. But it starts at 2 and ends at infinity. And between the maximum and the minimum points, that interval is described from -2, the x-coordinate of the maximum point, comma 2, the x-coordinate of the minimum point. If I was asked to describe the intervals where this graph is increasing and where this graph is decreasing, I would say that this graph is increasing in the first interval, the interval to the left of the maximum point, and that's going to be the interval from -infinity to -2. This graph is also increasing in the region to the right of the minimum point, and that's the interval from 2 to infinity. If I was asked to describe where this graph was increasing, because it's increasing in two disjoint intervals, we usually separate those intervals with a union symbol. I can kind of think of that as or. It's increasing in this one or this one. I guess and might be appropriate, but that's the symbol that we usually use. if it's increasing in multiple areas, regions. And then if I wanted to describe the interval where this graph is decreasing, there's just one of them. I would say this graph is decreasing in the interval -2 to 2. Again, these, when I'm segmenting the graphs into the regions, on either side of a maximum or minimum point, or between maximum and minimum points, I only use round parentheses. It's going to be important to be able to decide if a graph is increasing in an interval or decreasing in an interval by just inspection, and then with calculus. By inspection, if my marker is getting higher as I'm drawing the region, the graph is in an increasing interval. So this region, my marker is moving away from me. This region, my marker is moving away from me. Those are both increasing intervals. As I'm drawing this, my marker is getting closer to me. That's a decreasing interval. So putting all of those skills into a single problem, this is kind of where we're headed. If I give you a generic graph, here's a graph that has a relative minimum point at the point -8, -448, a relative maximum point at the point 252. We want to be able to describe the intervals where the graph of the function is increasing. We want to be able to describe the interval or intervals where the graph of the function is decreasing. I want to say the coordinate of any relative or local maximum point. I want to describe the local maximum value. I want to say the coordinates of any relative or local minimum point. Notice I would just switch the words seamlessly because they're interchangeable. And I want to say the relative minimum value. So to do this, I'm going to segment this graph into regions. I'm going to go to the region to the left of this minimum point. So this is going to be my first region that I'm going to try to describe. This is to the left of, that's clearly of a minimum point. And notice I'm not even saying maximum or local or relative. It's not kind of necessary. And I also need to focus on the region to the right of this maximum point. And I need to know the region between the maximum and the minimum point. And to describe these in x's, the first region is going to start at the far left edge of the x-axis, which has an x-coordinate of -infinity, and it's going to end at the x-coordinate of the minimum point, which is -8. So the first region is the region from -infinity to -8 in terms of the x's. The region between the minimum point and the maximum point starts at the x-coordinate of the minimum point, which is -8, ends at the x-coordinate of the maximum point, which is +2, all round parentheses when I'm trying to describe the intervals on either side of maximum and minimum points or between maximum and minimum points. And lastly, this third region starts at the x-coordinate of the maximum point, which is 2, goes to the far right edge of the x-axis, which is infinity. These are the intervals where I need to describe where the graph is increasing and decreasing. This first interval and this third interval, as I'm drawing my markers getting closer to me, these are both decreasing intervals. So when I go to answer the increasing and decreasing part, I have to understand that those are decreasing intervals. And the middle interval is an increasing interval because as I'm drawing, my marker's getting higher on my paper and moving away from me, whereas the outside intervals are considered decreasing intervals because my marker's getting close to me. So to answer the intervals where the graph is increasing, there's just one. It's the middle interval from -8 to +2. There's two intervals where the graph is decreasing. The far left interval, -infinity to -8, and the far right interval, 2 to infinity. Then it asks me to find the coordinate of any local or relative maximum point. I don't know how readable that is, but that's the point 252. And then it wants me to say the local or relative maximum value. The relative maximum value is the y-coordinate of the maximum point, which is 52. This is technically just y equal to 52 is the relative maximum value, which means any point close to this, its y is going to be less than 52. Its x's may be less than 2 or bigger than 2, but their y's will all be less than 52. And this is the way I usually write that. So rather than writing this down, this would be a better answer for part D. The relative maximum value is y equal to 52, which occurs when x equals to 2. For the relative or local minimum point, that's this point -8, -8, -448. And then the relative minimum value is -448, which means any point close to that, its y value is going to be bigger than -448. Its x's may be more, this x's may be less, but its y, the relative minimum value is y equal to -448 because any point close to it, real on either side of it, is going to have a y that's bigger than -448. This is not quite good enough for the answer. This is the way I should write the answer to what the relative minimum value is. We usually state the y and also tack on the x. So that's what we do in college algebra. And in calculus, we're going to kick up the difficulty because we're going to find intervals where the graph is increasing and decreasing. We're going to find local maximum and local minimum points without even having a graph in front of us. And that's from understanding what the slopes of tangent lines look like. Because in intervals where the graph is increasing, if you draw a tangent line, it has positive slope. We say in increasing intervals, slopes of tangent lines are positive, which means the first derivative is positive. Or the derivative in this case, we don't know. There's something called first derivative and second derivative, which we'll learn pretty soon. But the derivative is positive. Because in order to get a tangent line with positive slope, the derivative has to have a positive value at that point. Similarly, in decreasing intervals, if I drew the tangent line at any point, its slope is going to be negative. And in decreasing intervals, the value of the derivative is negative, because the value of the derivative is the slope of the tangent line, and lines that are drawn in that direction have negative slopes. This is a big deal. You don't really need to understand it. You can do the algebra or the calculus without understanding why, but this is going to be the why for the when we try to find intervals where a graph is increasing and the intervals where a graph is decreasing using calculus without having a graph in front of us. The concept is we're going to find the first derivative, and any intervals where the first derivative is positive, the graph will be increasing. Any intervals where the first derivative is negative, the graph will be decreasing. That's kind of the theory that's involved. I typed up probably too much, but I typed up quite a bit right here that I should talk through. So we're going to use calculus to find the intervals where a graph is increasing and decreasing and to find the local or relative maximum and minimum points. You see how I usually scrub the word local and relative? That's just lazy on my part, but I'll live with it. That's probably a common thing to do. So if I just have an equation and I don't have a graph, how do I find an interval where a graph is increasing or where a graph is decreasing? It's not particularly hard, but the first thing I do is I find the derivative of the function, and then I find the critical numbers for the derivative. The critical number for the derivative is any value of x that makes the derivative 0 or undefined. Let me start with this problem, and I'm going to try to show you without having a graph, and then I'll show you with a graph what I mean. So for this function right here, if I want to find the maximum point, the minimum point, where the graph is increasing and where the graph is decreasing without having a graph, the first thing I would do is find the derivative. So first, to figure out where this graph is increasing and decreasing, and where it has a maximum or minimum point, without having a graph staring at me, first I'm going to find the derivative of this. The derivative of this function is simple. The derivative of x cubed is 3x squared. The derivative of minus 24x squared is minus 48x. And the derivative of 18 is 0. So the derivative of the function is just 3x squared minus 48x. Now I'm going to find the critical numbers for this function. That is any number that makes the value of x equal to 0, any value of x that makes the derivative undefined. Derivatives aren't going to be undefined for polynomials, so here I'm just trying to find any value of x that makes the derivative equal to 0. So my critical number, these are the values where I could have maximum or minimum points. My critical numbers I get, in this case, because my function is a polynomial, by taking the derivative and setting it equal to 0. I want to say first derivative because pretty soon in this chapter we're going to find out how to take a derivative of a derivative, and we'll call it a second derivative, and that tells us something about the graph of a function as well. So I'm taking the derivative, setting it equal to 0. I'm solving it by factoring. I'm factoring out a common factor of 3x. When I factor out a common factor of 3x, I'm left with an x and a minus 16. These two values that I'm going to get, one is going to be the x value of a maximum point, the other is going to be an x value of a minimum point. For the factor of 3x, when I set it equal to 0, I'm going to divide by 3 and get x equal to 0. For the factor of x minus 16, when I set it equal to 0, I'm going to get x equal to 16. One of these is going to be the x-coordinate of a maximum point. The other is going to be the x-coordinate of a minimum point. I don't know which yet, but values that make a polynomial's derivative equal to 0 are always either the x-coordinate of a maximum point or the x-coordinate of a minimum point. So I found my derivative. I found my critical numbers by setting the derivative equal to 0. Now I'm going to do some testing to figure out if the graph is increasing or decreasing in the intervals that I'm going to create here in a second. How do I create some intervals? I'm moving on to step 3 right now. And for step 3, I'm going to be able to figure out where the graph is increasing and decreasing by creating a number line. And on the far left edge of the number line, I'm going to put negative infinity. On the far right edge of the number line, I'm going to put positive infinity. And between the infinities, I'm going to put the x coordinates that I just calculated for my critical numbers. So I took the derivative, I found the critical numbers. Now I'm plotting the critical numbers just on a one-dimensional number line that also has negative and positive infinity. Next, I'm going to create intervals with only round parentheses. These are going to be the intervals that go in the answer for either increasing in an interval or decreasing in an interval. So I'm going to get an interval from negative infinity to 0, from 0 to 16, and 16 to infinity. Done with step 4. Move on to step 5, and this is the ugly step because I can have a different step than yours. Our answer is going to be the same in terms of what interval is increasing, what interval is decreasing, but here I need to find in these intervals if the derivative is positive, meaning the slopes of the tangent lines are positive and the graph is increasing, or if the derivative in that interval is negative, meaning the slopes of the tangent lines are negative and the graph is decreasing. So in each interval, I need to pick a number. In my first interval, I'm going to pick 1. I'm going to pick negative 1. It's a small number, but it's in that interval. So negative 1 is not a critical number, but it's in the interval between 0 and 16. I can pick any number in this interval. I could have picked negative 12 if I cared to. In the middle interval, I'm going to pick x equal to negative 1. I just need any number, not 0 or 16, but between 0 and 16. And in the last interval, I'm going to pick 17. Again, I can pick any number that's bigger than 16 as my test number. I'm going to plug the number into the derivative. If it's positive, that means the slope of the tangent line at that point, that value of x is positive and the graph is increasing. If when I plug the value that I select into the derivative and get negative, that means the slope of the tangent line is negative and the graph is decreasing. So for each one of these, I'm going to say evaluate the derivative at negative 1, which will be 3 times negative 1 squared minus 48 times negative 1. Then I'm going to evaluate the derivative at 1 and do 3 times 1 squared minus 48 times 1. And then I'm going to evaluate the derivative at 17 and do 3 times 17 squared minus 48 times 17. And for each, I'm just going to get a value. Pull out my calculator to do these because I don't want to do these by hand. So first computation, lighting gets to be such an issue at times of the day. So first interval, I can't even see what I'm going to do, but it's going to be 3 times negative 1 squared minus 48 times negative 1. I get positive 51, means the slope of the tangent line at x equal to negative 1 is positive 51. That means the graph is increasing. If I get a positive number when I do the computation, the graph is increasing in that interval. Regardless of the number you pick, you're going to get a positive number, but a different positive number. If I put negative 2 in or negative 3 in, I'd get a different value for the value of the derivative, but it's going to be the same positive value telling me the slope of the tangent line is positive. Let me hit second and then my enter key. Brings up the line, and I'm going to delete the negative 1 and make it a positive 1. I'm going to delete the negative 1 and make it a positive 1. So I hit second and enter to bring the line up that I just typed. And this tells me when I plug in 1, I get negative 45, which that's the slope of the tangent line at that place. Tangent lines that have negative slopes go down. And so in this region, the graph is decreasing. I don't think I could use the second and enter trick so nicely to type 617 in because I have to use the insert key. I'm not good using the insert key. So 3 times 17 squared minus 48 times 17 gives me positive 51 again. This happens a lot because I pick my points kind of equidistant from the critical number that we get duplication in the values. That shouldn't surprise you. It's going to happen a lot. And because this value is positive, the graph is increasing in this interval. So because the slope of the tangent line is positive, the graph is increasing in this interval. So let me see how my steps, what I've done. So I took the derivative, I found the critical numbers by setting the derivative equal to 0. I plotted the critical numbers of 0 and 16 on a number line that also included negative infinity and positive infinity. I made the 3 intervals up. I picked a number in each interval, plugged it into the derivative, and I'm determined whether the graph is increasing or decreasing in that interval. The graph is increasing in the interval if you get a positive value when you plug the number in, the test number into the derivative. It's decreasing in interval if you get a negative number when you plug the test number into the derivative. So let me start to answer the questions for this example. So the derivative, f prime of x, is 3x squared minus 48x. That's the answer to part A. The critical numbers are x equal to 0 and x equal to 16. Got those in my first bit of algebra. And now I want to write the answer to part C. Well, this graph is increasing. Let me pull out a different color so maybe it'll stand out better. It's increasing in the interval negative infinity to 0, and it's increasing in the interval from 16 to infinity. It's decreasing in the interval from 0 to 16. The 0 and 16 are either the x-coordinate of a maximum point or the x-coordinate of a minimum point. So to answer the rest of these, I'm going to need to get some y values because I only have x values. And I need to know if I have a maximum or a minimum point, and this is real easy to tell. So moving on to my work right here, I've determined if the graph is increasing or decreasing. I'm done with my step 6. Now I'm going to place directional arrows in each interval to signify whether the graph is increasing or decreasing. So in my first interval from negative infinity to 0, the graph is increasing, so I draw a line that has a positive slope. In the middle interval, the graph is decreasing, so I draw a line that has a negative slope. And in the last interval, my graph is increasing, so that I draw a graph with a line with a positive slope. This is when I say place directional arrows in each interval to determine whether the graph is increasing or decreasing. Now, I'm going to figure out if the x-coordinate is a part for a maximum or a minimum. Super easy to tell. At x equal to 0, that x is going to be the x-coordinate of a maximum. At x equal to 16, that x-coordinate is going to be the x-coordinate of a minimum point. So I know that the relative maximum point is 0 comma something, and I know the relative or local minimum point is 16 comma something. I just need to get the comma somethings. So that's kind of where I'm at right now. I've determined that I have the x value of a maximum point and the x value of a minimum point. To finish up, I need to get the y coordinates of a maximum point and the y coordinate of the minimum point, and I get y coordinates by using the original function. In this particular problem, the original function is x cubed minus 24x squared plus 18. So to get the y coordinate of the maximum point, I'm going to need to do 0 cubed minus 24 times 0 squared plus 18. And to do the y coordinate of the minimum point, I'm going to do 16 cubed minus 24 times 16 squared plus 18. And I did this off screen when I wrote this example up. So let me steal those numbers. And I believe when I plugged in 16, I got negative 2030. And when I plugged in 0, I got 18. That's just calculator. Since I'm at 32 minutes, I didn't want to press buttons on my calculator, but you just enter these on your calculator. So the relative maximum point is the point 0, positive 18. The relative minimum point is the point 16, negative 2030. So let me write up the answers to what needs to be finished. I have all the algebra, all the calculus done that I need to do. I found the first derivative, found the critical numbers, wrote the intervals where it's increasing, wrote the intervals where it's decreasing. The relative maximum point is the point 018. So next to part E where it says what the relative maximum point is, I'm going to write the point 018. For part G where it says the coordinates of the relative minimum point, I'm going to say it's 16, negative 2030. And then for part F and part H, the relative maximum value is the y coordinate of the maximum point. The relative minimum value is the y coordinate of the relative minimum point. So the relative maximum value is y equal to 18. And usually we tack on the x. And so in this case, I'm going to tack on the x. I'm going to say which occurs when x equals to 0. Similarly, for the relative minimum value is y equal to negative 2030. And we usually tack on about the x, so which occurs when x equals to 16. That's all the theory in this section, but I'll do another example, but I can't do it. No, I guess we'll start doing the homework in the next part of this video, which is good because I just spent 34 minutes. This is all the theory that we need, and I'm just going to march through these steps for each of the problems. Each of the problems that we're going to do are going to ask the same A through H questions. Find the derivative, the critical numbers, find the intervals where the graph is increasing, the intervals where the graph is decreasing, the coordinates of the maximum and minimum points, and the maximum and minimum values. Some of the problems are just looking at graphs, and those are freebies.